Hello everyone, in this video we are trying to follow this book, Cloud-Based Remote Sensing with Google Earth Engine. We are following chapter A1.5 Heat Islands. This chapter is about the phenomenon called urban heat island, which is the most studied one. Here the cities are warmer than either its surroundings or an equivalent surface that is not urbanized, and we have known this effect for almost 200 years. The main cause of this effect is the urbanization. Urbanization is the replacement of any natural landscapes with man-made built-up structures such as buildings, roads, and parking lots. And urbanization can also change the properties of the land surface, modifying the local weather and the local climate. Challenges remain in the studies of the urban heat island. So the main being the difference in temperatures within the city, making it difficult to capture the urban heat island for the entire city, and also the values observed by satellites and those calculated using the air temperature measurements can be different. And there are two different products, the popular ones. The first one is the MODIS Terra and Aqua satellite products, and the second one is the thermal bands from the Landsats. So this chapter shares us the demonstration being done in the USA, and I can say the difficulty level of this chapter is somewhat medium. There are so many things to learn, and please go through the chapter ones if your main interests are in urban heat islands. So here we begin the first section of the codes. Here we have our region of interest. And here, this is inside the EE.feature collection. We have the path to the polygon or our main region of interest. So here we are using dot union. This dot union only makes the outer boundary appear, and not including the inner boundaries that might be present inside our main boundary. And then we have this map.setCenter fixing our main polygon somewhere in the center. And here we have the zoom level 12. And then we are adding this as the layer. So this is our area. And then we have the MODIS image collection. If we checked about this data set, we can see this is the aqua land surface temperature and emissivity at day global 1 kilometer, and we can also see this is depreciated. There might be some updates with the dates, but this is okay to use it for now. We have the bands here, LST underscore day underscore 1 kilometer, so the minimum and maximum values are here, and the description is dry day land surface temperature, and the scale is 0.02. the units are in Kelvin. We also have other bands, and we can explore if needed. From the MODIS image collection, we can select this band. This is the day land surface temperature, and here we are creating a filter by ee.filter.day of year, providing two different numbers, 152 to 243, and this particularly relates to the June 1st and August 31 in the normal years. So this is being set here as the summer filter. Then for that land surface temperature, we are doing this dot filter date from 2014 to 2019, and we also have this filter that is the summer filter. So we want to have our years filtered and also the days of year filtered. So every year we will have the images only from those specific months. And we are doing this dot mean. Dot mean averages all the pixels. So it just finds the mean of all those pixels from the image collection. And here we are multiplying it with some constant 0.02, And here we have this dataset, global surface water, selecting this band. So this is to exclude the presence of water from the land surface temperature image that we will be doing. So this will be used each time. So here now we continue clipping it with our region of interest, subtracting it with constant for converting to degrees Celsius, and we are updating the mask, so we don't want to have the water present in the land surface temperature image. And then we add this as the new layer, so we will see something like this. So we can see a striped type of image, the red meaning high temperature, and this blue color meaning lower values, and the white means somewhere between the higher and lower values. And to do this, we want to check this. If we do not do this dot union, what we see is the boundary inside the main boundary file. So that this is why dot union was done there. So this is for the MODIS dataset. We can also use the Landsat datasets for doing the land surface temperature, but the process is something different here. So we begin with this e.algorithms.landsat.simple cloud score, and this is the algorithm. So it computes a simple cloud likelihood score in the range 0 to 100 using a combination of brightness, temperature, and NDSI. This is not a robust cloud detector and is intended for mainly to compare multiple looks at the same point for relative cloud likelihood. So this algorithm just tries to detect if there is the presence of cloud or not. So we want to have anything less than 10 to be used, and this is drawn within the function. So this is just being used as the cloud masking function. There are other ways, such as using the quality pixels present within the Landsat datasets, but here the cloud masking has been done from this algorithm. Here we have the image collection, then we have this filter bounds, just to include the pixels, include the image present within those area or the area of interest. We're filtering it with the dates, so from 2014 to 2019. Here we have the summer filter to include the images only from the June to August, and then we are mapping the cloud mask. So this will keep something like this. Here we are printing this, and here we have 22 elements, and then we are generating the median image. So the median image is just similar to the mean image. The workings are similar. Dot median is used when there are extreme values such as clouds. And then we are selecting the band 10. This is being clicked for our main area of interest, and then again we are updating this not water, meaning we want to exclude the water pixels. And we can add this band 10 as the layer. So we will see something like this. So this is the Landsat band 10 here, and the book, the chapter has this nice explanation about this thermal band. So this is the brightness temperature. So this is the temperature equivalent of the infrared radiation escaping the top of the atmosphere, assuming the Earth to be a black body, and this is not the same as the LST, which requires accounting for atmospheric absorption and re-emission, as well as the emissivity of the land surface. And one way to derive pixel level emissivity is a function of the vegetation fraction of the pixel. And to define the emissivity of the surface of a material is its effectiveness in emitting energy as the thermal radiation. So some definitions, but to But in general, just to say that this band 10 is not exactly the land surface temperature. We need to do some processings to finally say it as the land surface temperature. So that is the main idea here. So we move further. So for that we will calculate the NDVI, and for this we are also doing the same thing, dot filter bounds, to have the images around that region of interest, filtering it with the dates 2014 to 2019, again filtering it with this summer filter, doing that median image gives the single image, and then we are doing this normalized difference. So this calculates the NDVI. We are providing the band 5 and band 4 and then renaming it as NDVI. We are clipping it with region of interest, and we are updating the mask. We do not want to include any water pixels. And then we see this NDVI. So we see this NDVI. So this is our usual NDVI here. And the thing to see here is that there are no green color at all. So this is the city area, and this is the reason why there are no green color at all. But the NDVI is doing its work, but we cannot see any green here. So this is the thing here, and we continue and we move further, and we find the minimum and maximum of NDVI. We combine the reducers for this. So here we are doing this dot reduce region for that NDVI image, and we are doing this first reducer, that is ee.reducer.mean combined with ee.reducer.max. So this is just for the efficiency, combining two different reducers within one function. Then we have this geometry, and then scale and the maximum pixels. So this will give something like this. We have the minimum and maximum printed here. So the NDVI maximum and NDVI minimum is something like this. And then we are getting the minimum and maximum value from that min max. And then we are calculating the fractional vegetation. So fractional vegetation is the fraction of ground covered by green vegetation. So it tries to do the spatial extent of vegetation. For that we are subtracting the NDVI to its minimum value and dividing it by difference of maximum and minimum and renaming it as the FV. And we can see this FV, and amazingly we can now see some green color. That means we are extending, or we are some type of magnifying the presence of vegetation in those areas. Then we have this emissivity calculations to be done. For that we are providing some constant. We can see this dot number with the numbers, and this is just do not mess with the server side and client side operations. So anything that has dot is the server side things. So everything is happening in the server side. So here we are doing A and B, and for that we are multiplying it with multiplying that FB with A and adding the B and renaming it as EMM. And we can see this here, and here we see some green colors, more greenery in that in the map. And everything that was shown earlier was, of course, for finding or calculating the LST from that band 10. And here is that equation. So here, this equation uses the band 10 and also uses that EMM, emissivity, and finds the land surface temperature. So this long process was done to find the land surface temperature. and we can add this as the layer. So this is the land surface temperature from Landsat thermal band, and we can check the two different images, one from the MODIS and one from the Landsat. So there are huge difference between the two land surface temperature images. The MODIS image is very coarse, we see nothing, we just see the stripes, but the Landsat best Landsat surface temperature, it's so refined, it's so detailed in it, so detailed, and we can see many things, many colors being arranged in that image. So this is the way to find the Landsat surface temperature from Landsat thermal band. To move further, the authors of the chapter also says this way to do the Landsat best Landsat surface temperature. Landsat based land surface temperature from this line here. This is the path to the written functions. So these are the functions that were already written, and we are just calling it and using it. So this is done by require, and this is the long path to the functions already being written, and we are providing the geometry, satellite name, start of the date to the end date, and we want to use NDVI. Yes, we want to use NDVI, and then we are using this to get the Landsat best land surface temperature. And then here we are selecting the LST, filtering it, finding the median image, clipping it for our area of interest, updating the mask, we don't want watt pixels, and subtracting it, and we add this as the layer. So that the process that we saw earlier, and this is the same. We are using the we are just using the function that was already written. We called it, and we used providing it with the parameters. To move further, we have other things as well. So the urban heat island is just to compare the temperature of the city areas with the temperature that are not exactly cities, or in the sense that we want to compare the temperature of the city areas with the temperature far from the city areas. For that reason, we create the buffer, and creating a buffer is very easy in our engine. That is done by .buffer, and here in this function we create the buffer, and we also find the difference between the geometry with the buffer and our original geometry. So here we are creating a ee.feature. This creates a buffer, and we are also finding a difference or subtracting with the original feature. And here this is being mapped to the area of interest, and we are adding this as the layer. And what we see is something like this. So this green color here is the buffer, or the subtracted area from that function that we did. And the approach that is suggested in the chapter is that that we want to have this similar surrounding or similar buffer here to have the equal area with our original region of interest. So we also want to have this this outer boundary to have the area equal to our main feature. So that is the main objective, applied main objective here. So for that we apply this ee.list.sequence. We do it from 30, value 30 to 3000 with the increment of 30, and this is the buff whites, the name is given. So this creates the sequence from 30 to 3000. Every value will have 30 added to it. So this is the nice way to create the sequence if we want in any other works. So here we begin the function buffer optimize. So it has the feature in it, and within this function we have another function. So here we are having the buffer length, and here we are doing the buffered polygon, and in this buffered polygon we have the geometry, and then we are doing this buffer with the buffer length, and we are resulting it with the property called the buffer length. So buffer white will have this buffer length, and then we have the area. So this buffered polygon we will consider it as the geometry. We'll have the difference subtracted with the original geometry. We are finding the difference between the buffered polygon and with the original geometry, and we are finding the area of that. And then here we have the different feature. So again we are doing this buffer polygon dot geometry, and then find the difference with the geometry. So three things are going on here. So we return this buffer difference, buffered area, and buffer width. So three things we are doing in the function, within the function, and then here we are applying this function to our original buff whites. That was the sequence. So this was the sequence here. So we are applying that function within this, and then we are also sorting it with the property that is the buffer difference. And then we have here this the first one being written, and then we will have this area, and then we have our buffer width. So let's try to understand what this function is doing. So the end goal of this function is to have the area as low as possible, in the sense to compare with the original area of the feature with the area of that boundary. So please go through the code once again. The objective is that thing, just to find the area equal, or the belt will have the area equal to the original feature. And what we see here, this has been applied to our main area of interest, and what we see here is something like this. So the first one was so here it's being loading. It's loading here. So and this is always not necessary. We can also use the land cover data. So this is the land cover data called NLST 2016, and this land cover from this land cover data set, we select the urban pixels, and then we have this applied to when you select those urban pixels, and also to select the non-urban pixels. And we can see these are the urban pixels, and we also have the non-urban pixels from those from the NLST 2016 land cover dataset. So two things we saw here. The first one was we created the buffer, and the second one was this function where we try to find the belt or the buffer in the bell set, which will have the area equal to the features area. And then we also used the land cover dataset to find the urban pixels and the non-urban pixels. So this is the conclusion of this section. And to move further, what it says is we want to calculate the summary temperature values for the urban boundary and the different versions of rural reference using the Landsat and MODIS LST. So here we have the function polygon mean. It takes the feature, and every time it takes the feature, for each feature it uses the Landsats and MODIS based MODIS created temperature, land surface temperature, and tries to find the mean from them. For example, here this is the LST final, we're subtracting it with the constant, and some mask has been applied just to exclude the water pixels. And then we are doing this dot reduce region to find the mean. And then we have this feature dot geometry and then scale. So this is repeated each time here using the update mask for urban. So just to have this urban mask, and then we do this with scale 500, and then we have this done for other areas as well. And here we are doing this with Landsat. And so this is just a way to find the different versions of things, different means from different areas using two different datasets, Landsats and MODIS. So this is the main objective here. And finally, the function returns these things. Here the function is returning the list of mean temperatures, and what we see here, if printed, is this one here, and also this can also be done for mean LST for different cases, just similar to the above one. And so these are basically finding the different means for different areas that was done earlier. And here we are printing all those results to understand further. The first one is this one here. So here we are seeing the mean temperature for different cases, such as Landsat, land surface temperature for rural, urban from MODIS, and for the urban mask and urban pixels. Then we also have this reduced rural, finding the MODIS based mean temperature. We also have this temperature for this one here, with buffer area, buffer difference, and this calculated temperature calculated from MODIS based LST. Okay, and then after, then the end goal is to find the difference between the rural based and the urban based land surface temperature. So here we are finding the difference between rural LST from the total LST. So here we are finding the difference between this one here with the subtracted with it with the reduced dot forced, and the reduced dot forced here is the Landsat LST rural pixel, and this will give something like this. So so these are the overall overview, preview of the chapter, and there are so many things to adapt, and we can adapt in our own analysis if we wish to. And I tried to go through the chapter. Many things might not have been that clear, but I hope I was able to explain things. So with this, I would like to conclude or end this video. So I would say thank you for watching. Thank you.